So I want to tell you a little bit about the Fermilab Muon program and making muons great again. Yep. All right. So what's with the title? I know some of you are here just to find this out. Okay. So I know we have a divided nation where I would claim we were divided up into three groups of people. First group is that says, when did the muons stop being great? I'm in that camp. Just like, I've always thought muons are great. The angry people are like, when were muons ever great? All right. And then the third group of people is, what the heck is a muon? All right. So my job here is to try to tell you what a muon is, get the third group of people up to speed, and then try to bring everybody together so at the end of the lecture, we all think muons are great. Whether we thought they were great before or not is irrelevant, but let's bring us together. Okay, so what is a muon? So in the 1930s, people thought they understood what matter was. It was very simple. It was your protons, your neutrons, your electrons, and everyone was happy. In 1937, they'd made a discovery that another particle existed that they call the muon, and it's a constituent that is showering down from above in cosmic rays. And what they discovered was this particle looks like a heavy cousin of the electron. It's point-like, it's got charge, but it's heavy. It's got a mass that's 2 times heavier than the electron. It's 105 MeV, that's 1 million electron volts. And that's the term that high-energy physicists use to determine mass. So it is also unstable. It's got a lifetime of 2 millionths of a second. Now, I tried to look up and try to get a gauge as to what 2 millionths of a second is. If you go to Wikipedia, it says that is the amount of time we subtracted off of the 24-hour day after the Japan earthquake, which I think Myra knows about. And so there are these little changes. It's not very much, but it's long enough for us to make the muon useful. And the other thing is when it decays into a muon plus an electron and a neutrino, anti-electron neutrino, and a muon neutrino. Now, when you see this decay, what you'll see is a muon and then an electron pop out. It's very difficult to see the neutrinos. So, but this discovery was extremely unexpected. Let's see if I can set this up. So we've got cosmic rays coming down, showering down on us right now. And we have this nice little demo. Okay, some cosmic rays. They're supposed to be coming down at about 1,000 muons per square meter, which seems to be, it's finicky now. So what you have here is a piece of plastic scintillator viewed by a sensor that actually can look at light. And when the particles come down, it excites the piece of plastic, and when it de-excites, it makes light, and the light travels down and is sensed in the photomultiplier here. And then you want to put them in coincidence because these things tend to be a little noisy, and you just want to pick up the particles that are true tracks. So when a part comes down and then hits this one, and you try to find a coincidence of when those things hit together simultaneously, and that's what you're seeing here. You can see I can put my hand over it. It doesn't affect anything. So that's why it's true that muons pass through, but they really don't interact very much. They just lose a little bit of energy. So in the picture, hold on for a sec. So we're just going to keep that going, and it didn't really quiet down, but that's okay. I mean, so in the picture here, you can see what's happening. High energy particles come down, mainly protons, nuclei, protons. They shower in the atmosphere. They create pions who decay, and then the pions go off and create muons, and neutrinos, muon neutrinos. And so something that lasts 2/millionths of a second you'd think wouldn't make it down here. But this is an example, a great example of special relativity. So I think people have heard that moving clocks move more slowly. So in the rest frame of your muon, it's 2/millionths of a second, but and it can only travel 600 meters. But in reality, when you have this time dilation, this lengthening of time, it lasts kilometers. And so when it travels down, it can travel and hit the Earth. So tens of kilometers. Okay. So the reaction from one of the Nobel Prize winning physicists was, who ordered that? I mean, this was completely unexpected. Who made this happen? You know, why is this messing up our reality? So apparently this is, so you can read this. It says, why are, we're creating the universe, and, we've added everything. We've added the forces. We're now getting to the particles, and now we're getting to the leptons. We're ordering. Here's the last invoice, Universal Particle Services, UPS. And we've added this in, electrons, and then muon, who ordered that? I can't wait to see it on their faces. And here they are scratching their heads, like, what the heck have they ordered? So, okay, well, I apparently ordered this. They do come, you can get your own muon in case you want one. Yeah, it's great. Let's see if I can get him in there. There's my muon. If you read the little blurb here, it says, a heavy electron who lives fast and dies young. He's part of a six-pack of leptons, which I only ordered the one. But, and it has the lifetime, and it says it's a heavy electron, but you can tell it's not too heavy, not too light. It's like a nice lepton. Okay. So, 80 years later, here we are, and we've measured these very precisely, the properties of the muon. We know it's got a spin 1/2. We know it's got a mass, and look at how precisely this is measured, this precision measurement. It has lifetime, again, in 10 to the minus 6 seconds. Muon magnetic moment anomaly that I'll talk about, this experiment that we're doing at Fermilab. And here is pretty much 100% of the time it's decaying into an electron, anti-neutrino electron, and a muon. So that's, that's pretty good for 80 years of study, but it's also can fit on one page. But just so you don't think that this is what we do, that we haven't done anything but that. This is our particle data book. It is giant. It is filled with lots of information. It's heavy. I still get the paper copy. Just, I don't know. I have like versions from past years. If you can see this. This is the type of stuff that we do. I don't know if you can see. It's got like lots of information. Okay. So, but we can do the Cliff Notes version. So, this is what we know. These are our known knowns. It's called the standard model. And I think most people have seen this. I mean, I don't think I'm telling you anything you haven't seen. We've got our 6 quarks, our up, down, charm, strange, top, and bottom. Top was discovered most recently. We have our leptons. There are electrons, muons, taus, and their associated neutrinos. So the bound quarks are fractional charge. They're bound together. So like a proton is made up of an up, up, down. So 2/3, minus 1/3. So you get your charged particles. They're governed by these bosons. The forces are governed. So your weak decay, your weak force is governed by a Z and a W. Your electromagnetic force is governed by a photon. And your gluons are the things that glue these quarks together, so you don't see any free ones. That's the strong force. They're spin 1/2 particles. These guys are spin 1/2. These are integer spin. And again, with the leptons, they can be free. You have charge -1, and for the neutrinos, you have no charge. So when I was a kid, when I was a student, at the standard model basically had charged leptons with massless neutrinos. We couldn't see anything that indicated that there was mass to the neutrinos. So the impact of that is that we also had no mixing in our charged leptons. And so the muons never could turn spontaneously into an electron. They could decay, but they couldn't turn into them. Well, recently, I mean extremely recently, there's been new physics found. And this new physics shows that the neutrinos mix. And so you can start out with a muon neutrino, and it can mix into an electron neutrino. So you can produce it, and then suddenly you measure it later, and it is an electron neutrino. And that's really startling. It impacts, first of all, it indicates that neutrinos have mass, and they can oscillate back and forth. It also, for me, impacts the charged lepton flavor violation. So something that had been assumed to be 0, actually, this imparts a little bit of lepton flavor violation, but it's extremely small, this by itself in the standard model. So this won a Nobel Prize for these two gentlemen. And it is new physics, which we don't get very often. So we love the standard model. We've tested it to death, but we also know it has deficiencies. And one of the obvious deficiencies is it's missing a big piece, which is gravity. We also know that there's indications of dark matter, like from the rotations of the galaxies, and that the universe is expanding out by some unknown force that they've called dark energy. So these are things that we believe exist, but the standard model that I've just described here only deals with this, the visible matter part. And so that's pretty startling. So we have lots of ideas as to what could possibly be going on and what these other theories, we're looking for a complete theory that it can encompass all of this, but we don't know which one of these theories actually is going to work. And so we need to figure out how to investigate that. So where are we going to go from here, and where are we going to search for new physics? I think a lot of people, or certainly people in this room that are physics aficionados, know about our direct searches. So what we do for the direct searches is we try to get as high an energy beam as possible in order to produce really high mass particles. And in 2012, the last piece of the standard model puzzle, which is the Higgs boson, was discovered at these ATLAS and CMS experiments at CERN. So CERN is this large, at CERN there's a large hadron collider, and it's in Geneva, Switzerland. And what they did, what we did, was you smashed together two beams of particles that were like 7 TeV, so not a billion, but a trillion electron volts. And, I'm gonna go back. There you go. And we try to reconstruct those particles and see if we can find that when you were reconstructing it, that they actually form a specific mass. And we had no idea what the mass was going to be. But what you try to do is you put them together and then you plot them out, and you're seeing, is there anything that there's more prevalence, like where you can actually, where it occurs more often. And by doing that, you can get a mass peak. And that's effectively what we've got here. We've got a bunch of background. And this tiny, tiny little mass peak right here at 125 GeV. And that was pretty astounding. And it was the result of a direct search. So this is new physics that we can produce directly. But there's another way of searching for new physics. Oh, no, another Nobel Prize. They give it to the theorists. They didn't give it to the 6,000 experimentalists who worked on it. They give it to the theorists. It's okay. They deserve it. They deserve it. So, so the indirect searches. So this is the other method that you can do. So the way that we do indirect searches is we compare theoretical predictions with what we measure. And so an example of this, I had to dig around for a good example that I could explain. So in the same way that you have a bump when you have the Higgs mass, there's a particle called the Z boson, and you get a bump for that, and that's what this is. right there. I should do it with this. So the Z is decaying into fermions, and so you can have it coupling to the quarks, you can have it coupling to the charged leptons, and also to the neutrinos, but you don't get to see the neutrinos. And so what we do is we have an absolute width, we have a width that's a composite of all these things, and we can calculate the widths of our quarks, the widths of our neutrinos, and the widths, the contribution of the widths from the charged leptons, and you add them up. But you can change the number, because we don't see the neutrinos, we actually weren't sure how many generations of neutrinos we had. We knew, this was before they found that there was an actual tau neutrino, and it was distinct from the muon neutrino and the electron neutrino. So we were just trying to see how many generations there are. And so by adding in these different contributions, you can predict, you can see which model the data follow. And so here, it says here, average measurements where the error bars have been increased by a factor of 10. You can see how tiny these little error bars are. This is the data. Those little red dots are the data. And you see it fits best to the 3-generation model. And you see here the number of neutrinos for the number of generations is 2.984, whatever, and it's very precise. So, what's the result? No new physics. We did that a lot. It's like, but it's okay because we need to check to make this, make sure we understand the standard model. So now we're going to move on to another set of experiments that rely on the muon. So why are muons really good tools to study for this? And one of the reasons that we like to use muons is we can produce copious amounts of muons pretty easily. They're long-lived, so we get a chance to study them. They're charged particles. We can bend them in magnetic fields and steer them. We can accelerate them. It's easy to make them polarized. And so I want to say that you want to make you want to take a particle where you can understand its beginning state. And you can do that with a muon, and I'll tell you how we can do that. The other thing is that muons decay into electrons, and electrons are extremely easy to detect. And in addition to that, why we think this is a great probe is because because the muon is heavier than an electron, it turns out that it's more sensitive to these little fields that we could be probing for new physics. So for those of you who are in Illinois and northern Illinois and have the chance, I suggest that you go and visit Fermilab. This is our laboratory. It's in Batavia, Illinois, outside of Chicago. It's really lovely. And these are the 2 experiments that I'm going to talk about today. The G-2 experiment, which hopefully by the end of the lecture you'll understand what I'm talking about. And this one is again, we're going to use 2 different methods to search for new physics in this indirect way. One is through precision measurement of G-2, and the other one is to search for rare processes and that one is the Muon experiment. And that's the experiment I work on. Okay, so muon magnetic moment. I think people are used to spinning tops, and what happens with a spinning top? You have it spinning very tightly, but then gravity starts to exert a torque on it, and it starts to wobble and precess, and it can stay that way for a long time because it's spinning, and it won't fall over until it slows down. Okay? Well, a muon has a magnetic moment like a bar magnet. It's an internal, has a little internal magnet. So the way that in classical physics you think about it is you have a little ball of charge, and it's spinning really fast. And that's almost like having a little current loop. And with a current loop, it forms a magnetic field. And so you can think of it like a bar magnet. And like the top, when you put it into a magnetic field, it wants to precess. And so G is this gyromagnetic ratio, which is determined by the strength of the magnet and the rate of this gyration. And it turns out that G equals 2 to within 1/10 of a percent. Now, you're like, okay, that's good enough. Well, the physics is in this number. And so we're going to study that. See, sorry. So now I'm going to see if I can actually talk and do this thing at the same time. Probably not. It's like chewing gum. Hold on. I did not do this well earlier, so we'll see if I can do it. Okay, so here's your spinning top. And we're going to start up. It's got a little magnet on the top. Okay. And now we're going to pulse it with like a little magnetic field, and you can see it precess. Except I didn't spin it heavy enough. Let me try it again. All right. So the magnet's right up on top here. Am I the only person who's not? There we go. There we go. So you can see it precessing. And that's exactly what we're going to be looking at. Okay. So in measuring G minus 2, if it were identically 2, when you have your muon traveling with momentum p and with the spin aligned with that direction, if G were exactly equal to 2, when you put into a storage ring with a nice uniform magnetic field in a donut shape, you will have it exactly traveling around and it will never change direction. Okay. But what we know is that it actually isn't 2. It's just slightly different from 2. And what you'll find is as it goes around, so the spin, the frequency of the spin and the frequency of it cycling around, it slightly precesses and it will kind of walk away from the direction of the muon momentum. So how do we do the measurement? Well, we have a muon that has a spin, and it decays into an electron. Again, I have to use that. So so it decays into a neutrino, electron neutrino, an anti-muon neutrino, and a positron. So I didn't mean electron. So the spins it turns out that the neutrinos have what's called a handedness. They want to have their spins, as far as the neutrinos go, anti-aligned with the momentum that they leave with. And with an anti-muon, it wants to have the spin in the same direction as the momentum that it leaves with. Well, those things cancel, and what you're trying to do is preserve this spin from the muon and conserve it. And so that implies that the positron carries away exactly the spin of the electron. So that's great, because you detect this, you don't detect this, you detect this, so you'll know if you detect that and you can figure out the spin, then you'll know exactly what the spin is for the muon. And so that's what we do. Your muon's going around in the cyclotron, is basically going around in the storage ring. It decays, the neutrinos carry away a little bit of momentum, the positron starts to bend inward in the magnetic field, and then it hits this calorimeter. And you can actually see that the energy is varying, and the variation of that energy distribution is governed by your spin frequency and your cyclotron frequency. And what happens is, if the spin is aligned with the momentum of the muon, it gets to higher energy, and if it's slightly precessing away, then you get a lower, and that's what you plot out. So I'm a physicist and I have to show plots, but you're not supposed to take anything away from this other than this is, what you see is your decay of your electron, your standard lifetime of your electron, and then you see these little wiggles, and that's what you're measuring over many, many lifetimes of this particle. So, and these are 4 billion decays. This is the data set from the previous measurement. It's quite beautiful. And they do this 5-parameter fit across this. Okay, so this measurement has been done previously, and the most recent one was done at Brookhaven. That's Brookhaven National Lab. And they had a really nice explanation that I think will bring everybody up to speed on what we're doing. So you take protons, you run them into a target, and you produce pions. You produce lots of things, but you can produce pions. The pions decay away. Oops. And pions spinless. Again, you have a muon neutrino that has a very well-defined spin that goes opposite of its muon, opposite of its direction, and then that implies that your muon neutrino, or sorry, your mu plus has a very well-defined direction because this is spin 0, and so you create this beam, and which you can see here, where the spins are all done in the same way. They're all lined up in the same way, and then you inject them into a little storage ring. And the storage ring has a very uniform field, and they precess. And you're going to measure the precession. So here they are. They're precessing away. After each circle, they're changing by 12 degrees, and it keeps traveling around in a circle. Many times, each time, muons are decaying. And as they decay away into the electron then will carry the information about the spin of the originating muon. And that's what you measure in your little, your detector. Oopsie, there we go. So, this was muon G minus, this was the experiment at Brookhaven. It's this nice little storage ring. It's a beautiful experiment. It did a great measurement. It also, so they turned off the beam in Brookhaven and decided not to run it. But at Fermilab, we thought this is a great experiment. We'd actually like to collect more data on this. So let's move it. So so let me go back through what Brookhaven measured. So at Brookhaven, they measured again, I'm not used to this. They measured this number. Remember I said it was 1%? There's your 1%, right there, or 0.1%. And then there's a bunch of numbers beyond here. And this is the theory, which is also 0.1%, and there are a bunch of numbers. And you can see that the numbers are identical up until this point. And then the difference is very, 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 very tiny. And these things in the parentheses are the uncertainty of your measurement. And the difference between the numbers is 3.6 sigma. And I'll describe to you what a sigma is. But it hints of new physics, but it's not conclusive. So to set the scale, when we discovered the Higgs particle, we demanded a 5 sigma, the signal above background was 5 sigma. So we have pretty high standards as to what is a discovery. So to set the scale, so this is what your measurement distributions look like. So you've got your theoretical predictions. So I think people know when they measure things over and over and over again, you'll get a distribution. You can't measure things exactly the same each time. So with the experiment, what you quote is a central value. So the central value is here, and the central value is here, and these are the errors. So here's the central value, and this is the width of that distribution. Here's the same with the theory. Okay, so are they the same number? I said that there's a very tiny difference. Is it the same number? There is some chance it is the same number. You see here that the distributions can overlap. But to set the scale of a 3.5, 3.6 sigma difference, that's 1 in 2,000 chance that it's not that's the same number. Well, that's not good enough. That's like the frequency of one event, one day out of 6 years. That's not that rare. We know that's not that rare. So what do? What we're trying to do is we're trying to get to the 5 sigma discovery. The 5 sigma is 1-day event out of all of recorded history, and then we know that we've got something worth talking about. So how do we do that? Well, we need to narrow up these distributions. So this is if the central value is exactly the same, but we need our measurement errors to be smaller. And we do that by getting more data. So you just measure it more times, and you can actually narrow up that distribution. You get a better beam of muons. You need to make your, what's called systematics in our term, you need to make sure that your measurement tools are very precise and known very well. And you do that by getting a better uniformity to your magnetic field and better monitoring of that field. And you need to improve your detection. And if you can, you'd like to improve this distribution at the same time so you understand it very well. So again, what we're trying to do is take this number and improve it so that it's, much better. So a factor of 4. Instead of, right now, this number is 540 parts per billion. That's how well we knew it. And we're trying to get it down to 140 parts per billion. And that's pretty precise. So that's why we want to remeasure G minus 2. So we took the ring apart. So the thing about this experiment is the magnetic field, the very beautiful uniform magnetic field. It is a great, great magnet. So this is a superconducting magnet. Superconductors, I think people know about superconductors. They are made of a certain material so that when you cool them down, the resistance goes down. It helps save on our electric bills, but it also means that we can have higher fields if we need them. People use them for MRI machines, and I think people are pretty familiar with them. So what they tried to do is they went through the effort of moving this ring from Brookhaven, which is on Long Island, out to Fermilab. And they did this. They used a company, Emirate Corporation. They've actually moved the space shuttle before. I mean, they are used to moving big things that are very delicate. And so they built this red frame. And these are your superconducting cores. There are actually 3 of them. There's the 3rd one. And they kept them because they had to make sure that they didn't move at all. So because if you break it or damage it, you're stuck. So they went through and moved it. And they started out by actually moving it from Brookhaven down out Long Island to a dock, because we're going to ship this by water. You can see the guy, they were doing it like 20 miles per hour. You can see him walking along next to it. I guess it's slower then. He's not rocking at 20. But and they wrapped it in plastic because they didn't want it to get damaged and water damaged, and they advertised their little company on the end. You can watch this guy jump up on, where is he? There he is. He's jumping up because he had to go through a toll booth. And now they're really cranking. They're at 20. All right. It'll stop. It'll stop eventually. But it's pretty amazing that they had to do this. They had to close down the road. And this is in New York, on Long Island. It's not close it down, but, stop it. And then, okay, so then they parked it. So here they are. They moved it from 3,200 miles by boat. And they moved along the coast. They had to park it because a storm came up. And so you couldn't have it tilt more than 30 degrees, and it had to be within, I want to say, 1/10 of an inch. It really had to be very, very rigid, and so that you didn't damage the coils. So, and this is a big 50 diameter ring. So here it is. I'm a St. Louis girl, so I like seeing the arch. So there it is. It's going up on a barge. There it is. It's made it up to Illinois, up the Illinois River, and they had to open up the bridge there. And then it showed up to Fermilab. And so there was a big party. I mean, I was amazed. Apparently, along the way, people would just come out to watch it go past. They parked it in like a Walmart or something. They parked it in parking lots, and people would just come and see it and get their pictures taken next door. But there was a giant party. And then they took it off to a parking lot or next to a building because the building wasn't ready at Fermilab. So they parked it for a while, but eventually the building got done. So this is the Muon campus. Again, I keep on going for this. This is the Muon campus. There's the Fermilab high-rise. This is, the shot before was actually from over here. It's looking towards it, but this is behind. And you can see there's the building. So now you have to reassemble it. And so here's the picture. There's the steel. So I didn't talk to you about the steel, but it's 750 tons, and only 17 tons of it was the coils, the superconducting coils. So here it is. I had like this area here. Originally it was a ring, and then they took this stuff out, and I realized only late that it was because they had to get in and out of there to put the scaffolding up to get this thing in. So they put a bunch of steel down because that's where the magnetic field lines go. You want to get it uniform. You want to put it back together just as you found it. And the frame comes down. I keep on seeing these lines, and I'm old school. I thought originally it was like scratches on film. No, that's a rigging for the crane. And so then the frame isn't needed, so it disappears. And now they start stacking up more steel. I think this took about a year to put back together. It's like a big jigsaw puzzle. But it has to do, and they moved the thing with the cryo. You know, it's cooled with superfluid helium, and they left the cryo connections here. But you can see it, and you can see the coils there. Oop, it was supposed to finish. Sorry, people. Could go back. I wonder if I can do that. I wonder if I can go out here. Let's try it again. Sorry, I hit the... Almost done. But this is only the beginning. So they get it all together, and then the hard work starts, even though this was hard. All right, there it is. Okay. So there's your collaboration, or part of the collaboration. It's about 200 scientists are in this collaboration from 8 countries and 34. That's typical high-energy physics. In fact, this is small. I mean, CMS and Atlas, they're like 3,000 scientists each. I mean, this is small, but it's still formidable. Okay. I think I told you that how you want to deliver muons to, when we did this at Brookhaven. So at Fermilab, the key is that we want to have a very clean beam. And so they deliver the protons, they strike on a target, you're making your pions will decay away, and by having them circulate down this long area, and they circulate, and by the time they are done circulating, you basically got a very pure muon beam. And then you deliver it to this experiment, which says MC1, that's the G-2 experiment. And you're going to detect stuff from there. So you're injecting muons at 3 GeV. They're like 6,000 muons per beam extraction every 10 milliseconds. And you're going to go and let these things decay away in your storage ring. So in the lab frame, instead of being 2.2 microseconds lifetime, it gets extended to 64.4 because of time dilation. So it circulates the storage ring about 400 times. And then you probe the lifetime. Sorry, that's the equivalent to 400 times, but you know it's an exponential decay, so you actually get more circulations than that. And you're going to continually probe the muon spin as it decays away over at least 10 lifetimes. And so this ensemble of particles, this collection of particles, you're going to be looking at the lifetime of all the decayed particles from the electron, or from the muons. You put it into a very uniform 1.45 Tesla magnetic field, and then you're going to look at the decay products of the with the electron and with calorimeters to measure the energy, and then tracking stations to look at where the beam spot is. So something that's different from the Brookhaven experiment is that they put their their tracking detectors inside the vacuum. So the muons are injected, but they're injected into an evacuated tube. And you do that because you know it's going to you don't want it to interact at all. So, and you also want it to continue to circulate. And so by putting these in, you can actually determine the position of the beam spot better by putting them into the vacuum. And you need that because you want to know exactly what field the muon is seeing as it goes through. So this is just to let you know, this is actually has been, these are the tracking detectors, these are the tracking stations. And it's actually already installed. So there are, and this is the calorimeter, and I think one station now the calorimeter has been installed so far. And this is the, okay, so this is the really cool part. So the magnetic field is the thing that you care about the most, and you want to make sure it's very uniform. So we put it together. This is what the magnetic field looked like, extremely uniform around the circular ring. That's the Brookhaven measurement. Well, when we put it together at Fermilab, this is where we were. And you can see it's not that uniform. So now we have to try to make it a better experiment by shimming it. So this is what these guys did. They're incredible. The way that you can change the magnetic field is by adding material. You add steel. And they had to do this. So they are 9,000 pieces of little tiny shims. This has the curvature of the ring, which you can barely see, of the storage ring. This is the 50-foot across storage ring. And they went through, they measured it, they determined what kind of shimming, what kind of extra material they needed, and then they put this in. And so what you're going to see is this team of people worked over a year getting this to flatten out. So you can see the excursions here are like plus or minus 600. These are parts per million. Okay, so you can see the magnetic field's flattening, flattening, flattening. So they're shimming, shimming, shimming. 9,000 pieces. And you can see the date. It's like taking years. Or a year. And so now it's flattening out. They're doing better. They're doing about as well as they did at Brookhaven, but that's not good enough. And so now you can see it. It's finally flattening, like, and now look. Okay, so here's your Brookhaven measurement. They changed the scale. I don't know if you saw that at the very end. And this is your, so this is your Fermilab. And look how flat that is. That's plus or minus 2. It went from like plus or minus 600 down to plus or minus 20. So that's pretty amazing. And these kids, so I thought, okay, you're going to destroy a bunch of students. They're never going to want to do particle physics, ever, ever, ever. Okay, you do something like this, it's like mind-bogglingly tedious. These kids apparently thought this was the greatest thing. So I think it helped that they weren't just shimming, because this really would be mind-bogglingly tedious. What they were doing is they were shimming, and then they were going back and doing another measurement. And then they got to analyze the data and see, okay, I have to put a little bit more shim here, a little less shim. Well, you can't do too much less shim, but you have to put more shims in and then flatten it out. So that I thought was really incredible. And again, it requires a very precise alignment, where it's a thousandth of an inch over tons of steel. So I think that this is kind of remarkable. So what's the status of our experiment? So the ring is cold, and they're going to take data very, very soon. where they hope to have a couple of weeks of data by the early summer, and then there's going to be a shutdown, and they're going to analyze that data just to make sure that they don't have any other adjustments to do on their detector and on the ring. And they hope next year to collect the same amount of statistics as the original Brookhaven experiment, which would be great, and then they're going to take additional statistics after that. So we should, if we're going to see new physics from this experiment, we should be seeing it very, very soon. So that's exciting. So I'm going to switch gears and talk about my experiment, mu to E. So mu to E stands for muon to electron conversion. This is the spontaneous changing of your muon into an electron, not through a decay. Okay, again, the size of the collaboration's very similar. We come from 6 countries, 37 different universities and laboratories. We're very proud of this. We had our building opening last month. People have been working on this project, I think, since 2007. It actually had started out as a proposal at Brookhaven, but then it didn't get approved. And then we picked it up at Fermilab and changed a lot of things about it. But people have been working on it for a very, very long time, and we're not going to complete it until 2021, and then we'll start to take data. So it's a long haul. It's typical for high-energy physics experiments. But you can see here, we have this area where it's basically going to be, it's very empty, and it's going to be filled up with our detector. Okay, so what's the physics that we're trying to do here? So we're looking for this charged lepton flavor violation that is extremely tiny. We think that by using a muon and making muonic atoms, we'll be able to probe these fields of the nucleus, and it's more likely to see new physics. So we know our standard model physics, but we're looking for things beyond that. The way that you do that is by looking at interactions with virtual particles that reside in the vacuum or in the nucleus. And by doing that and finding this, it'll be an indication of new physics. So we're searching for this, and we're searching for it to convert directly without any other things. Again, this is with the mass of the neutrino not exactly 0, which we know it isn't from neutrino oscillations. The prediction is that the charged lepton flavor violation branching ratio is 10 to the minus 53. Okay, that's really small. So my husband did this quick calculation. He's like, if you had muonic atoms, if every molecule or atom in the sun were a muonic atom, you'd only get 400 events. You'd only get 400 of these things coming out. That's a lot. We're not going to be able to probe that, okay? We're not trying to probe 10 to the minus 53. We're actually trying to probe new physics. And with new physics, you'd get an enhanced branching ratio of 10 to the minus 16, which still sounds small. But it turns out that's something we can actually produce and manage. So this one, not so much, but this one, yes. With our experiment, we expect, if it actually has a probability of having this happen at 10 to the minus 16, we expect to see 4 events. So that's pretty good. If we don't see it, then we set a new limit. Okay, so we're going to produce muonic atoms. So basically, an electron from the atom is replaced by a muon. The muonic atom actually has a lifetime of 0.864 millionth of a second. And the energy of the electron that's going to pop out is 105 MeV. So what do we see when we look at these muonic atoms? We can see the muon interacting with the nucleus and producing a neutrino and a neutron, and basically making an excited atom. That's not a background for us. You can see a decay in orbit, so you're now all experts at muon decaying into electrons and neutrinos. That happens a lot. That is a large background for us. Or you can see the signal. And the signal is going to be the muon spontaneously changing to an electron and with the nucleus, just in the presence of the nucleus. And again, the current limit that they have set in a different experiment, syndrome 2, is 10 to the minus 13. So that's pretty good. but we're trying to probe to the 10 to the minus 17 level. So 10,000 times better. So this is what our data is going to look like. This is right now, it's Monte Carlo. We're just simulating what our data is going to look like. Where now, you know that there's going to be lots of background from these decays and orbits, and that's what you see here, is large, large backgrounds. And then we'd see a tiny little signal, and that at 105, this monoenergetic, but you have the resolution of your detector, which broadens this. So instead of being a single peak, it's broader. So that's what we're hoping to see. So how rare is this process? Well, it's pretty rare. So if we had to set the scale, it's estimated that there are 1 billion grains of sand, and we're looking for like 1. Okay, so it is extremely rare. So how are we going to do this? So this is our experiment. It doesn't look like most experiments. I mean, I think people are maybe used to looking at like these large cylinder experiments where you're crashing beams, or with fixed target, I'm used to having something that projects forward, so you smash something in and your particles project down. This doesn't look like any of that. It is a fixed target, but it's got this other weird shape here that looks like an S. So I'll explain to you why we do that. Okay, so we're still going to produce, we're going to produce and fire 1 trillion protons at our experiment in order to make 10 billion muons. We have to pulse it in order to reduce our backgrounds. And so this is the beam that we're trying to produce, is a blast of particles and then dead space and a blast of particles. And we need the dead space to get our backgrounds to disappear. So we do this by, we make a muon beam by putting our target inside our solenoid. This has not been done before. The reason we do it is because we can actually get a more intense muon beam. So the previous experiment that set the 10 to the minus 13th limit, they did it by putting out a target. I think this is just also kind of standard. You blast your proton beam into a target, and then you try to capture some of the beams of muons down in this solenoid. Well, that only gets you have to have a very intense beam of protons, and you don't get that many muons. What we're trying to do is we're trying to confine our particles into this with a magnetic field to collect more muons, and we can actually reduce the size of reduce the energy of our beam in order to do that. So this is our target. It looks like a pencil. I mean, literally, there's like you see the pen there? That's the size of it. It's made with tungsten. When you take a beam and you blast it in there, it produces lots of stuff. Most of the stuff goes forward, and then there'll be stuff that goes backwards, and that stuff will collect into a magnetic field. I'm trying to figure out if this is the time when I should do my demo. Yeah, okay, so this is what a sample or prototype target looks like, where you're heating it up. It's also in vacuum, because you don't want to have your particles scattering. So it's hard to cool things down when they're in a vacuum, so it's a challenge. So we've been doing lots of tests with that. But this is probably the best. Unfortunately, you can barely see it. So you take the beam, you run it into your target, and you produce lots of different types of particles, but you produce pions, which will decay into muons. And so the lines in blue, which I hope you can see, are the pions, and then as they travel along, they decay into a muon and neutrino. And so by the time you get outside here, you get basically a beam, or actually here, you get a pure beam of muons. So that's the idea, but I'm going to try my demo. So this entire experiment relies on capturing these things, and you capture them, capturing the charged particles, and you capture them by using magnets, which I think at this point you're all experts on. So the key here is we actually have a graded field, and that sort of can push the projector, acts to push the particles back towards the lower field region. And so you can actually see this here, and they will spiral. And so I'm going to show you what a beam of electrons in a magnetic field spiraling will look like, if I remember which. There it goes. So there's your beam of electrons, and then you start to turn up the field, and it spirals tighter and tighter and tighter. And that's what we're relying on to capture it. So it's V cross B. It's the right-hand rule for people who know that. Okay. So, oh, I was going to show you. This was actually for the G-2, but we also use, I should have shown this before. That's your superconductor. We have something similar, it's just wrapped differently. Those are your superconducting wires inside with an aluminum extrusion, because you need the aluminum to basically to conduct the cold, and then because it's a good thermal conductor, and because you're trying to keep this at superfluid temperature, so to reduce the resistivity of the superconductor, and then you pot the thing in epoxy, and that's what it looks like. And ours are similar but large. Okay, and we produce 75 kilometers of superconducting cable, and we're going to have 28 meters of superconducting magnets. I don't know if this is like the largest. Myron's nodding. It probably is. I mean, I don't know. I didn't get out much. So, oops. There we go. So now you've got your spiraling muons. You've gotten rid of your backgrounds as best you can, and you're trying to get the slow ones, because you want to stop these things in material to create muonic atoms. You need to get the to have them slow down, and you select that, and you stop them in these thin foils of aluminum, and you create muonic atoms, and then the electrons popped out. So red is for the muons, and blue is for the electrons that are decaying in the field of the nucleus. And the reason that you do this beam you do the pulsed beam, is because you get a spray of particles, and you don't want to see that in here. You've got enough problems back here to begin with. You really do not want to see all of these particles that are produced by the proton beam, because you just get things in your activity in your detector that you don't want. What you do want is you're going to let your muonic atoms try to decay away. That's your decay in orbit. You still have background from that, but hopefully it won't be as bad as the beams flash. And then you've got this little tiny signal right there. And so this is a cartoon. This is not to scale, right? But you're trying to dig out a very tiny signal on a lot of background, just like you had to do with the Higgs. So, and other backgrounds that I'm not going to talk about. So, once you've produced your electron, you need to look at the momentum, because that's our critical measurement for this experiment. And you do that by looking at the curvature of the particle in this magnetic field. And by doing that, you can actually determine what its momentum is. And so you use a bunch of tracking detectors. Again, this is all in vacuum. We're using straws just the way that G-2 did. And once you've done the momentum measurement, which looks like that, again, we're trying to get to this signal region. That's what it looks like. Okay, so this region, oops, here is our search window. So you just integrate over that. If you were to integrate over the whole thing, that's how busy it is. And that's not even near the flash windows. This is how many hits we have. But if you look within a little tiny region in time around where our signal is going to be, you can see, and you like little snippets of time window. You can clean that up a lot, and you'll see your electron track. So We use a calorimeter behind the tracking station because we want to actually reject backgrounds again. And it's critical for looking at distinguishing between muons and electrons. And then, just like over there, we have a bunch of cosmic rays coming down, mimicking our signal, which is a real drag. So what we do is we put a box, basically this a cosmic ray telescope, just like that, into our detector. And it's giant. So there's like a little picture. Oh. So you see here, that's a human being. This thing is giant. This is like a football field's worth of material. And they're like little pieces of plastic. They're extruded. You can see that? It's clear. Just like those pieces of scintillator, it's a piece of scintillator. They extrude it. So there's this machine, which I don't know, again. It extrudes with the plastic scintillator and the coating around it simultaneously, and it blows the holes in. So what you're trying to do is you're trying to put fiber. So it creates a photon of a certain wavelength, and then you have to shift it into a region that you can detect. Okay, so what's the status of my experiment? It's still in it's now in the construction phase. We have our building. Our solenoids, our giant magnets, are being fabricated because those are the most complicated things about this experiment. The detectors are being, the designs are finishing, and we're going to start constructing them soon. And then we're hoping to, we're planning to start commissioning the detector in the building in 2021, and then we're going to start a 3-year physics run to reach our design sensitivity. So, Big Bang Theory. Why am I showing this? So, David Salzberg is a physicist who's a consultant for Big Bang Theory. Whenever you see these things on Big Bang Theory, they're real. I mean, I don't know if he's come to talk to you guys or not. Anyway, they're real. He goes in and makes sure that all the physics that's shown in that show are correct. So he writes on this whiteboard. And he's been great for particle physics, absolutely great. He's a great spokesperson for that. And it's great, it's like product placement. It's been great. So he called up our spokesperson, Doug Lenzinski, and asked for a favor. He couldn't remember some story that he wanted to actually incorporate into the show. And Doug tells him, repeats the story. He goes, oh yeah, okay, now I remember. So Doug says, well, now you owe me. You need to try to incorporate mu to E into Big Bang Theory. And we're like, oh, this is going to be great. And David's like, oh, great, okay, I'll do it. We're like, this is going to be great. Here's the top. That was what David worked on. He was like, here's the top. Everyone knows about the top. This is going to be great. And everyone's going to know, they're going to be talking about mu to E forever, right? Well, he tells us when the show is going to take place. And we all watch it. We all tune in. I taped it. And I'm like, okay. Where the heck is the whiteboard? I'm like, oh, wait a minute. It's all the way over there. Oh, I'm just like, oh, and if you know what you're looking for, it's great. It is true. That's really us. You've got like a muon converting to an electron with this new theory, which is heavy neutrinos that happens at 10 to the minus 13. I'm like, he did what he said he would do. It just wasn't quite the advertisement we were hoping for. So I'm hoping it didn't burn up too much of our 15 minutes of fame because we really need it. So, but we were thankful that he did it. So in summary, we're heading into a new era of muon physics. Again, I'm hoping I got the third group of people up to the level at least of understanding what a muon is. And maybe we can all get behind the muon now instead of being so divided. I was just showing this, and then maybe we're all hoping that we'll have new physics coming out of this program, and we're looking forward to our 15 minutes of fame. But I wanted to show you this beer bottle. So the story behind this beer is that when the ring moved, they were looking for some way of advertising it, which is great. And so the project manager for G-2 called up the local beer company, two brothers that are in Warrenville, which is right next to Batavia, said, "Oh, can you help us advertise it? We're having a party at this thing. I'll pay, I'll pay for you to have this, but can you think of a new way of doing it?" So they made a beer for us that's called the Magnetic Moment. Very cute, and it's got a lot of physics actually in this one label. But so we're hoping once we discover the new physics that they'll agree to help us out and do more clever things. They also have Atom Smasher beer, which is, I don't know. So, all right, this is like the don't throw things at me. Boo. Oh dear. All right, I'll end on this note. Thank you.